MOS Small-Signal Model. The quadratic characteristics described by equation along with the voltage-dependent capacitances derived above form the large signal model of MOSFET. Such a model proves essential in analyzing circuits in which the signal significantly disturbs the bias points, particularly if nonlinear effects are of concern. By contrast, if the perturbation in bias conditions is small, a small signal model that is an approximation of the large signal model around the operating point can be employed to simplify the calculation. Since in many analog circuits MOSFETs are biased in the saturation region, we derive the corresponding small signal model here. For transistors operating as switches, a linear resistor given by equation together with the device capacitance serves as a rough small signal equivalent. We derive the small signal model by producing small signal increment in a bias point and calculating the resulting increment in other bias parameters. Since the drain current is a function of the gate source voltage, we incorporate a voltage dependent current source equal to GM-VGS. Figure A. Note that the low frequency impedance between G and S is very high. This is small signal model of a ideal MOSFET. Owing to channel length modulation, the drain current also varies with the drain source voltage. This effect can be modeled by a voltage dependent current source, figure B, but a current source whose value linearly depends on the voltage across it is equivalent to, here you can see the figure, a basic MOS small signal model. B, channel length modulation represented by a dependent current source. C, channel length modulation represented by a resistor. D, body effect represented by a dependent current source. A linear resistor tied between D and S. The resistor is given by R0 is equal to dou VDS by dou ID is equal to 1 by dou ID by dou VDS is equal to 1 by 2 nu n C naught x W by L VGS minus VTH whole square into lambda similar to 1 by lambda ID. As seen throughout this book, the output resistance R0 impacts the performance of many analog circuits. For example, R0 limits the maximum voltage gain of most amplifiers. Now recall the bulk potential influences the threshold voltage and hence the gate source overdrive, as demonstrated in an example. With all other terminals held at a constant voltage, the drain current is a function of the bulk voltage, that is, the bulk behaves as a second gate. Modeling this dependence as current source connected between D and S. Figure D, we write the value as GMB VBS, where GMB equal to dou ID by dou VBS in the saturation region. GMB can be expressed as GMB is equals to dou ID by dou VBS. Is equals to nu n C naught x W by L VGS equal to VTH minus dou VTH by dou VBS. We also have dou VTH by dou VBS is equals to minus dou VTH by dou VSB is equals to minus gamma by 2 phi f plus VSB or minus 1 by 2. Thus as GMB equal to GM gamma by 2 root over 2 phi f plus VSB is equal to eta GM, where eta is equals to GMB by GM. As expected, GMB is proportional to gamma. Equation also suggests that incremental body effect becomes less pronounced as VSB increases. Note that GMV GS and GMB VBS have same polarity, that is rising the gate voltage has same effect as rising the bulk potential. This model in figure D is adequate for most low frequency small signal analysis in reality. Each terminal of a MOSFET exhibits a finite ohmic resistance resulting from the resistivity of the material and the contacts, but proper layout can minimize such resistances. For example, consider the two structures of figure repeated in figure along with the gate is turbo resistance. We note that folding reduces the gate resistance by a factor of 4. Here you can see the figure reduction of gate resistance by folding. Shown in figure, the complete small signal model includes the device capacitances as well. The value of each capacitance is calculated according to the equations derived in session. The reader may wonder how a complex circuit is analyzed intuitively if each transistor must be replaced by the model of figure. The first step is to determine here you can see the figure complete MOS small signal model, the simplest device model that can represent the role of each transistor with reasonable accuracy. We provide some guidelines for this task at the end of chapter 3. Unless otherwise stated, this book we assume the bulk of all NFTs and is tied to the most negative supply, usually the ground, and the P, and that of PFTs to the most positive supply, usually VDD. Thank you.